I know these videos are not the most popular thing in the entire world because you don't like to have to do stuff, but they can be helpful for reviewing basic math things so we don't have to waste our time in class doing this. And this video is like the epitome of that because this is a review of honors level gas laws, which was like one of the easiest things that we do in honors chem. Like algebra 1, pure and simple. So hopefully it'll be okay. First thing that we want to review is what is pressure, what causes pressure. So gases are different from liquids and solids because gas molecules are really far apart, they move independently from each other, and they're constantly trying to expand. So the only thing that keeps them from expanding infinitely is being trapped inside of a container or like gravity or something like with the atmosphere. So the measure of pressure comes from molecules bumping into the walls of the container that they're in. The more collisions there are, the higher the pressure. So you can change either of the two things, force or area, and you can affect pressure. So if we make the area smaller, that means there's going to be more collision, so the pressure would go up. If we make the force greater, so we add molecules or we speed them up because with like temperature or something, that's going to make them have a higher force and that's going to make pressure go up. And vice versa, you can do the same thing to make them reduce. You can take away force, you can increase area, whatever. Essentially, anything that you do that increases the number of collisions inside of a chamber is going to make pressure go up, and anything that you do to reduce the number of collisions is going to make pressure go down. So before we get into this, pressure, like even more so than some other things, has a lot of different units that it can be measured in, and I think that comes from the fact that like every culture and every society, we're all figuring out pressure semi around the same time, so they all had a different way of measuring it, and instead of everybody like universally switching to one, they were just like, yeah, we'll just use all of the units because that'll make all the kids have tons of fun in class. So we do have to be prepared to convert between units depending on what a question asks you for. If you look at page 197, we've got all the basic units like millimeters mercury and atmosphere and all that stuff. And we're going to convert between them the same way we convert between anything. You start with the number in the question and then you use the two conversion units. You set up a fraction and then multiply and divide. So for example, if we want to take PSI and turn it into millimeters mercury, the conversion ratio between them is 760 to 14.7. So we're going to multiply and then divide, and you get 6,820, if we round for sig figs, millimeters mercury. Okay, one more example just in case. Let's say we have 30.44 inches mercury, because why not have metric and standard in the same unit? Woohoo! We want kilopascals in the table. It has regular pascals, but we really just need to move the decimal place to make it a kilopascal. So instead of 101,000, it's 101.325 for every 29.92 inches of mercury. And again, we're going to multiply and then we're going to divide, and that's our answer. 103.1 kPa. Woohoo. Okay, so again, we have to be able to do that because obviously these questions are kind of silly, like there's no point to them, but there are going to be questions later where we're going to be using equations and constants that have certain units in them and whatever. So if you're given a problem that gives you atmospheres, but the constant that you need to use is in kPa, you'll have to do a conversion before you can put a number into an equation, so we have to be prepared to do that. Okay, one other thing about gases that I want to clear up before we review the gas laws is the idea that it does not matter what the gas weighs, it only matters how many moles of it you have. So for example, helium, nitrogen, and methane all have a different mass, but if you have a mole of them, then because you have the same number of molecules of these gases, all of the values for volume and pressure and temperature have to be equal. So this is one of the things that Avogadro kind of put together when he was coming up with all of his ideas about moles, is he's the one who like studied gases and figured out that if you have the same number of moles of a gas, then the conditions that they're in must be equal. And I know that seems counterintuitive because force implies that mass matters, but we're going to talk about why we don't need to worry about that in a unit later on. All you need to be able to remember right now is that it does not really matter what gas you have, it only matters how many moles of it you have. So the first relationship that we talked about in honors chemistry was that volume and pressure are inversely related. So if you look at the picture on the left, if you reduce volume, pressure goes up because there's more collisions. And the way that we represented that was something like this in honors chem. So the idea is if you have a large volume, the pressure is not very big, but if you reduce the volume, the pressure is going to increase. So they are indirectly related to each other. The second idea was that volume and temperature are directly related. So if you want pressure to stay the same, but you're increasing the temperature, that's going to make collisions go up unless you give them more space. So if you're increasing the temperature, okay, we represent it like this. So if we start with small volume, small temperature, if you increase the temperature, the volume is going to have to go up with it in order to keep pressure the same. And the last one that we talked about in honors chem is the idea that pressure and temperature are also directly related. So if you have an initial pressure at an initial temperature and you change one of them, the other one has to change in the same direction. So if we start with a low temperature and a low pressure and then we increase the temperature, the pressure is going to go up. Okay, volume stayed constant for these two examples right here, but the pressure is going to increase in the one on the right because the molecules are now moving faster because of heat, which means there's going to be more collisions. The way that we put it all together, the beauty of all these gas laws is that they work together. So we didn't learn those equations independently, we learned them combined. So we learned that if you have an initial pressure, an initial volume, and an initial temperature, whoops, that's a 1. Okay, then if you change something, they changed it this way. So you don't necessarily have to have all 3 units at the same time. Let's say you're given a question where you only have pressure and temperature. Then that means you can just ignore volume. What that's implying is that volume stays constant. If you have a question that does not mention temperature, so let's say now we have no temperature, then just leave it out. You have P1 V1 equals P2 V2. So every single combined gas law question essentially gives you at least 3 pieces of information and you're just looking for the 4th piece. For example, one of my favorite things about this chapter is how ridiculous all these questions are, and I just decided I'm not going to change it to make it make more sense. I'm going to leave it the way it is, because why wouldn't a snorkeler take a syringe filled with 16 milliliters of air from the surface to an unknown depth? I don't know. I do it all the time. So we're going to set this problem up the way it's asked, even though it's totally ridiculous. Okay. So we have a syringe. It has 16 milliliters of air in it. It's 1 atmosphere of pressure. So there's no mention of temperature in this question at all, which means I'm just going to stick with P1, V1, P2, V2. Okay, this is just implying that temperature must stay essentially the same the entire time. So we start with 1 atmosphere and we have 16 milliliters. On the other side, it says we change the volume to 7.5. What is the new pressure? And that is how we set this question up. So we're going to multiply and divide and solve for P2. So our milliliters cancel out and we are left with 2.1 atmospheres of pressure. There was a secondary part to this question in the book that asked if the pressure increases by 1 atmosphere for every 10 meters, what depth did he dive to? So he started at 1 atmosphere of pressure and went down to about 2 atmospheres, which means that he probably dove to 10 meters. So he was already at 1 when he was at depth 0. He went down to 2 atmospheres, and apparently every 10 meters you have 1 atmosphere of pressure. I don't know why they felt like they needed to add that to it, but yeah, why not? We'll solve it. Okay, one more. So some of you might remember this, some of you won't. Okay, but now we have volume versus temperature. There's no mention of pressure, which means we're going to leave P out. So this equation is going to be V1 T1 equals V2 T2. Here's the problem. It says that this gas, whatever the sample of gas is reduced to 0 degrees. And if we put 0 on the bottom of a fraction, we're just going to get an answer of 0. And some of you, again, may remember, this is the problem. So Celsius can be 0 and negative, which means we need to try to use a unit that cannot ever be those things, because if we have a negative number, that's going to make everything negative, and if we have 0, it's going to make everything 0. So we have to switch everything to Kelvin by adding 273.15. Every time you solve a gas law problem that has temperature involved, you must switch it to Kelvin. So we set this problem up with Kelvin as our temperature, cross multiply and divide. We were looking for the original temperature, which was 297.6, but what we need to remember is that that is now a Kelvin unit, so we have to subtract 273.15 to bring it back to a normal value. So 24.4 degrees Celsius would be the initial temperature. And the last concept for this video is actually something new that we're introducing for AP, which is the idea that moles and volume are related. So if you look at the picture, the idea is if you want pressure to stay the same, well, adding moles is going to increase collisions unless you do something to compensate for that. So the picture is showing that if you double the amount of molecules, then you also need to double the amount of space that they have. So this is V1N1 equals V2N2. So if we start with low volume, because there's not very many moles, if we increase the number of moles, the volume is also going to increase. If we look at one of the other questions, from example questions from the book, so we have male athletes' lungs, they're 6.15 liters when they're filled with 2.54 moles. And it says that they shrink to 2.55 liters. Okay, how many moles did he exhale? Well, in order to figure out how much he lost, we have to figure out what the new number of moles is. So we're going to cross multiply and divide for N2. So after exhaling, he has 0.105 moles left in his lungs. The question asked how much did he exhale? So our final step is to take 2.54 minus 0.105 to get our final answer, which is that he exhaled 0.149 moles.